which is about the smooth sequential optimization with delayed feedback. So Srivas, if you're ready, the floor is yours.
Hello, can you hear me?
Yeah, no, perfect.
I'm sorry, my Zoom quit out right at the right moment. So let me just share my screen before I get started. I think I might need
Should be a co-host and can share.
There we go. Okay, can you see my screen?
Yes.
Super duper. All right, thanks everybody. Yes, I did hear earlier about it being late in Europe and I'm in London. So as you can see, I'm trying to put on all the lights in my room to make sure it's not too dark. But anyway, thanks for the organizers for having me. I'm Srivas and I work in machine learning at Apple. So really what I want to do today in this short talk is kind of leave you with one or two interesting ideas about how these questions around estimation and questions around interpretation or interpretability that have been touched upon in the previous talks kind of come together in lots of real world situations. And my talk is very much focused on practical questions, and I'll be using mostly numerical simulations to get the idea across. And the kind of key idea I want to talk to you about essentially is to do with sequential methods. So what do I mean by that? Essentially, in a lot of contexts, in examples that have been touched upon actually, we want to learn about things as we go, right? It's quite a common theme. And this is why Bayesian methods are often very useful and interesting. And well, an application of the notion of learning as we go is experimentation, certainly causal experimentation, like randomized controlled trial or A/B testing, as it's called in the industry setting, where we want to measure differences between alternatives that we're interested in learning about. So that's one sort of context. Another context is where people want to sort of maximize yield in the real world context. This can be applied in industry, in clinical medicine, where you want to sort of exploit the things that is better as much and as early as possible. People often refer to this kind of problem framing as a multi-armed bandit problem, where you're trying to exploit as well as explore the world or the environment that the agent, which is because it's seen as a reinforcement learning problem, that the agent is sitting in, so as to maximize long-term value. Now, these sort of problems have been very well explored, and I don't think there's much to say that you guys don't already know. But essentially, our interest was somewhat slightly sort of complementary to that, which is, can we sort of somehow achieve both objectives? Because in a lot of contexts, people who work on reinforcement learning don't necessarily ask questions around experimentation. But when you're doing an A/B test, you tend to say, well, you don't violate causality, you run an experiment, and you look at the result. So that sort of is also nice, but in a lot of real world contexts where, especially in industry, where we want to get a bit of both, because there are reasons for having a trade-off between these. The question is, how can we do a bit of both? Because obviously, if you experimented only, you would learn a lot about the alternatives, but you wouldn't be able to exploit the best one. But if you explored the best one all the time, you wouldn't learn much about the alternatives. So here, I'm going to just quickly focus on the questions around Bayesian inference to achieve some control of that balance. That's kind of the main aim here. So first of all, some context around why we would like to achieve this sort of trade-off in the industry setting. One reason is basically because there's always humans in the loop. This is where the interpretability aspect comes in. Because these human operators are often there, involved in business relevant interpretation and higher order decision making. For example, deciding whether to add or remove treatments in the middle of an experiment. That's a very common scenario. And hence, we want to find some set of tools and technologies that enables human operators to maximize yield in the long run by essentially enabling interpretable learning. So while the learning about alternatives is going on, human operators should be able to intervene. Of course, this comes with challenges, which is something I'll speak to as we go along. But on top of this, there's also real-world engineering challenges to deal with. So what do I mean by that? One particular problem is something called delayed feedback. So let me sort of use some terminology here to explain exactly what that is. So in a lot of these sequential learning problems where we use this multi-armed bandit sort of terminology, we imagine these treatments as arms, and your agent is pulling the arms as you go along. And between consecutive updates of learning, essentially the agent is having to pull many arms, and you've got a certain batched sort of period between which the agent has to pull arms, and every so often it gets to learn something new. And that's because ultimately there's going to be delays in the real world. Now, the issue here, of course, is that these responses that are generated by the arm pulls from the real world, the environment is generating those responses, but they incur a delay. So it takes some unknown delay process before that response is visible to the agent. So for example, you can imagine a kind of Poissonian delay over time that decides when a response is seen. Each individual response is delayed by a different amount, and that follows a certain distribution over time. And the agent is pulling arms. Now, it's too restrictive to wait until all the delays have resolved themselves and we can see all the feedback. We would like to sort of build a system where you can update your knowledge as you go. We can decouple the learning cadence from the structure of the delay. And you want to sort of learn from the information that's partial at any given time. And we also assume that essentially this partial information is anonymous, because from the perspective of privacy, from the perspective of anonymity, all we're essentially assuming we can see is that at every update, the agent is seeing a certain composite summary of all the responses received since the last update, but it doesn't know which assignment or pull of an arm to a treatment produced that particular response. All you're seeing is a composite. So this, as you can imagine, imposes quite a few constraints on the learning process when you're talking about a sequential system, which is trying to, at any given time, at any given update, provide meaningful information. So for example, if one were to sort of imagine thinking about what sort of estimators make sense here, a standard maximum likelihood estimator, just to start very simple, produces interesting dynamics. So what I've done here is set up a simple simulation where I've got two alternatives with different rewards shown in blue and orange. The true rewards are, of course, unknown to this agent that is trying to learn them. And then at the same time, while trying to learn them, trying to also shift traffic allocation or shift the sort of treatment, as it were, to the best alternative. Now, what happens because of the delayed feedback is interesting. Essentially, the delay is in feedback, which essentially lead to partial information being available at any update, mean that for a while, there is overflow and underflow of information about any of the either of the two arms in this example. And as a result, maximum likelihood estimates are unstable, and this produces effectively a learning system that constantly oscillates, switches between thinking about which one is the best arm for a while till the delays can resolve themselves. And that's why you're seeing these unstable dynamics. Of course, we still learn the best one, but for a while, certainly human operators would struggle to imagine and try to understand, right in the first sort of 50 updates, 100 updates, which of these arms is the best one, because it's not easy to tell. Certainly, it can't be used for reliable decisioning, sort of higher order decisioning. So trying to sort of think about better estimators, something that's already come up, is obviously useful here. So if we think about the problem as trying to learn about these unknown rewards, the maximum likelihood estimates are, of course, as I said, noisy, but we can try and bring some more information in to help us alleviate that challenge. So firstly, thinking about it from a Bayesian perspective, we start by representing the uncertainty in our knowledge. That's the first obvious thing to do. And in this case, we can imagine two arms, the ones like I showed you before, where the one that has been pulled more, as in more treatments have been assigned to that particular arm at any particular time, it will have less uncertainty. In this case, in this example, if we pull the blue arm more often, we will imagine that the blue arm has less uncertainty around its our estimate around its true reward, as it were. Now, what we then do is, of course, look at a variety of different estimators. And in the interest of time, I'm just going to focus on the empirical Bayesian shrinkage estimator. And this, of course, as many of you I'm sure know, has very nice sort of properties around that basically bring frequentist ideas to play in the Bayesian context, where by constructing first an empirical Bayesian prior from the observed data in the past, we can basically then restructure or reorder or sort of shrink, so to speak, the means of the the maximum likelihood estimates towards the empirical Bayesian prior as a function of how much uncertainty there is in those means. So in this example, again, because the blue alternative has been sampled more, we're more certain about it, and hence we shrink it less. very standard sort of Jameson estimation going on here. But what we then do on top, and this is where we enable the delayed feedback to be handled nicely, is to apply smoothing kernels. So again, a sort of a practical extension, which allows us to basically take those empirical Bayesian estimates and then apply a layer of smoothing over time on those estimates. Now, what that gives us essentially is that we're able to trade off with the control of the kind of smoothing we're able to do over past empirical Bayesian estimates. We're able to trade off that speed versus stability of adaptation. And then, of course, one can use things like Thompson sampling and other estimation, other sort of traffic allocation or arm pulling methods on top of this to then achieve a different sort of adaptation that I show you in this picture here. So what you're seeing here is the same sort of situation, the same example, but with a different sort of estimation method involving empirical Bayesian smoothing. We get a much sort of more gradual, as you can clearly see, it takes slightly longer for the adaptation to happen early on. It's more gradual, but it gets to a point where the evidence is clear quite early on as to which arms are likely to be the winners. Now, so needless to say, we've got more examples from a larger set of contexts with many variants, many arms, many variable types of delays in the kind of Poissonian structure of that delay. And in all of these cases, essentially a common pattern is that this empirical Bayesian methodology, which is kind of well known to act as a strong regularizer, that essentially gives us a very useful feature, which is that it is producing stable, but essentially those slower, stable adaptation that enables the adaptation itself as the process as a whole to be smoother and more interpretable compared to, let's say, a maximum likelihood, sort of a frequentist standard maximum likelihood estimate, which does adapt, but essentially adapts in a much more noisy way. And the reason for this is also probably not that difficult to understand. Because of the delayed feedback, maximum likelihood essentially is unable to estimate accurately the arms rewards, especially early on. That's the issue. Whereas because the empirical Bayesian regularization essentially allows us to then apply a more gradual, stable, smoothing structure on the reward estimation process, we're able to then build a stronger estimator, especially in cases when the delayed feedback is adding noise. And while all of these examples here are showing you situations where the true rewards themselves are stationary, I'll come to a situation where you'll see that when the rewards themselves are changing, these advantages become much more pronounced. But before I go there, I want to come back to something I said right in the beginning, which is interpretability. Because in addition to changing treatment allocations and managing the maximization of yield of some objective, we also want to enable hypothesis testing that is also sequential. That is, at any given point, an experimenter could ask, what's the likelihood that one arm is better than another? So that then they might decide to remove one arm and then add a new one to sort of then essentially explore that instead of the one that is decidedly poorer. Now, how do we do this? So, of course, there are many different ways to attack this problem. We've taken a Bayesian approach to solving this, where we use Bayes factors. Again, that's a well understood idea that borrows Bayes' rule, makes it a relative likelihood ratio formulation, and then allows us to, at any given point, take those reward estimates we've got, and then construct a Bayes factor based on the likelihood that one of two hypotheses, one that the two arms have the same reward, another one, the two arms have unequal rewards. One can establish a Bayes factor that compares these hypotheses to each other, and then we can sort of surface a standard decision rule on top, which is again a topic that's been talked about, sort of using a standard sort of Bayesian decisioning process to be able to then expose to an experimenter these Bayes factors as a means to support decisioning. Now, of course, one would ask the question naturally, how do these Bayes factors behave over time in a sequential context? And perhaps unsurprisingly, what happens is because smooth empirical Bayes is doing this interesting thing where early on it's exploring the arms in any given experiment more often, it produces stronger and higher Bayes factors when there is a true effect. Effectively, what does this mean? It means that we get more statistical confidence to underpin those decision-making elements that we'd like to support the human operators to be able to do. So like, for example, as I said, arm addition and removal and so on. So very specifically, to sort of put it exactly in numbers, what we see is when you've got these sorts of more robust estimators, you're increasing the power of a statistical test. There are more true positives being detected and fewer false positives being generated. So this is essentially kind of, again, coming from the same reason, of course, which is that the empirical Bayesian method is providing a common substrate for better balancing exploration and exploitation early on, so that it focuses its sort of exploration strategy on the best sort of candidate set of arms rather than just going for the best one. And that actually is very useful in a lot of multi-arm bandit contexts, where while yield maximization or regret minimization is important, we also have other aims when we run these sorts of experiments. So finally, in the last few minutes that I've got, I want to sort of cover this simple example of modeling non-stationarity. Now, non-stationarity obviously is framed in the negative, and hence it includes a large set of possibilities of what do we mean by non-stationary. But I'll sort of end my talk with a simple example where we've got piecewise stationarity, where there's a change point, in this case at update 100, let's say, halfway through an experiment, there's an abrupt shuffling or change in the true rewards, which of course our agent has to learn about. So we're assuming, of course, of using smooth empirical Bayes here. And let's imagine that for simplicity, we have a smoothing kernel of size 50, which is flat. And in this situation, what of course is going on is, as time passes, the smoothing kernel is passing over the data, over that change point. And as the data accrues before and after the change point, the job of the agent is to figure out that the change has happened and shift traffic allocation to the new best arm, of course. And in these sorts of situations, it's very clear that the standard maximum likelihood estimation approach just leads to way too much instability, because ultimately the varieties of different sources of noise that are getting added, one being here these changes in the true rewards themselves, plus on top the delayed feedback that's always going to be there behind the scenes, is causing so much instability that it's difficult for the maximum likelihood estimator to tease those apart. So in contrast, what we're seeing with the sort of smoother empirical Bayesian estimation is, while it's a bit slower, as is clearly evident, it's more stable in picking the best arm and sticking with it once after that change point sort of update 100. So this trade-off essentially is what we'd like to sort of highlight, where you've got a slower but more stable adaptation and with a lower variability in estimation error, which we get with alternative estimators, like in this case, the empirical Bayesian one. So really, to conclude, and I think I'm mostly on time, I'd like to sort of highlight and summarize 3 key points. Firstly, that this sort of smooth empirical Bayesian estimators can help us produce more stable adaptation, especially under the kind of real world conditions that constitute what we see with delayed feedback, where information isn't always available when you want to update and learn new things. What do you do then? These sorts of estimators can become very useful, and kind of the Bayesian idea that sort of underpins our estimation methods become really valuable. Secondly, it's not just about estimation. As I've shown you, Bayesian hypothesis testing or sort of decisioning can also be sort of facilitated by these sorts of empirical methods. And ultimately, the reason for this, which I want to leave you with, is because empirical Bayesian methods explore weaker arms early on a bit more, enabling us to learn about their value, and then sort of tail that off as a function of the signal to noise in the data. And ultimately, as a result of all of these things, it enables better handling of the temporal variability in true rewards, which of course is much more realistic, because in almost any real world scenario, one can't assume stationarity to persist for very long. And hence in these contexts, it enables us to balance the stability versus speed of this adaptation, because ultimately that control enables us to build systems that enables humans who use these systems to use them better. That's it. Thank you very much for your time.
Thank you, Srivas. Thank you very much. So we have 5 minutes for questions, if anyone has some question.
How many actions are you using it on typically? Is it you're looking at very large numbers of actions, or is it suitable, say, for recommendation where we have, you know, really millions of or if they're combinations that, you know,
that's a very good question. So my perspective on that is, this scales very nicely as you increase the number of actions. But when you get into the orders of millions, a hierarchical method, something I haven't talked about today, would be the kind of natural extension of this idea, where you're able to group your estimates based on the structure of some sort of pre-existing knowledge of your contextual bandit sort of setup. And that would basically be my sort of way of thinking about millions of arms, as it were.
Okay.
So certainly a standard empirical Bayesian approach would be the building block, but I don't think we would stop there.
Okay, thank you.
Any more questions?